Hi everyone, this is Mrs. J, and today we're going to talk about how derivatives affect the shape of our graph. Alright, I have a warm-up for you guys to try, so please pause the video and give it a shot. Alright, go ahead and check here. So you can see I found the zeros by factoring our original function, setting equal to 0. So we have 3 zeros here at 0 and then plus or minus root 3. So remember that's a little less than 2 and a little bigger than negative 2 for root 3 and negative root 3. And then to find the local maxes and mins, I found the derivative and set that equal to 0. So we have critical points at when x is negative 1 and when x is positive 1, because that's when the slope of our tangent line is 0. So if you plug those x values into our original function, we get these two values. So we get negative 1, 2. So if you plot that, you'll see that it becomes a maximum. And you have 1, negative 2, which will become a minimum. And then you kind of connect your dots, and your graph will look something like this. And then you can see here, here's a graph of our first derivative. We know that it's equal to 0 at negative 1 and 1. And this is just a parabola whose vertex is at 0 and negative 3, so you can see that here. And then I found the second derivative. It's just 6x, so notice I did rescale my y-axis to help me graph it. So it's going to be extremely important that we start understanding the relationship between the derivative and the graphs. So let's take a look at this first graph right here. And we're going to kind of think about it in context to its derivative. So we're going to first see if we can determine the interval or the intervals where our derivative, our first derivative, is positive. So meaning the slope of our line is positive, so it's increasing. So you'll see here that actually there's a little horizontal line. We actually flatten out, so it's actually 0 here, here, here. Notice here we come to a point, so remember that a point or sharp corner, our derivative is undefined or does not exist. It's kind of hard to see, but it also flattens out right here. So I can see that my derivative would be positive in this region, then again here. It does hit 0 for a second, but then it continues being positive. You see it's positive here, and then the rest would be negative or 0. So those intervals would be from A to C1, and then from C1 to C2, and from C3 to C4. And then if we are looking at the intervals where our first derivative is negative, remember that means our slope is negative, or our graph is decreasing. So it would be here, here, and here. But again, we don't want to include this area because it does flatten out, but then it continues staying negative. So we have C2 to C3, and C4 to C5, and then C5 to B. And then we're going to list all of the values where our derivative, our first derivative, is 0, which is, again, when the slope of the tangent line is 0. So that occurs at C1, C2, C3, and C5. Remember, we're not going to include C4 because our derivative is undefined here. And then we're going to look at where our derivative would change from positive to negative. So that would be right here at C2, and then also here at C4. Because to the left of C4 we're positive, and to the right we are negative. So when we see something like this, you'll notice that we do have a relative maximum. And then let's look at the times when our derivative changes from negative to positive. So I can see that that's happening here at C3. You can see on our graph, when that's happening, we have a relative minimum. And then what happens if the sign doesn't change? So where is that occurring? Well, that's occurring here at C1, and it's also occurring here at C5. So when even though it does turn to 0 momentarily, if it continues staying the same sign, you'll see that it actually is neither a minimum or maximum. Neither min nor max. But again, you can see when our derivative does change sign, we have some type of relative, minimum, or maximum. All right, and now we're going to start generalizing what we know about our first derivative and how that is related to where our graph is increasing or decreasing. So we know, what can we generalize about when the function is increasing and the first derivative? We know that our function is increasing when the first derivative is greater than 0 or positive, and we know when our graph is decreasing, that means our first derivative is negative or less than 0. So you can see that from the previous slide, our first derivative, where it changes sign, it can give us an idea of where a maximum or minimum might occur. So that might occur at that critical number, essentially, and a critical number will be where your derivative is 0 or undefined. And a derivative also might tell us where our function might change from increasing to decreasing or vice versa. And again, that will always occur, that changeover point will always occur at that critical number, which is where the derivative is 0 or undefined. So now we're going to kind of tie that all together, and today we're going to be focusing on first doing a sign analysis of the first derivative and what it tells us. So a sign analysis of the first derivative can tell us whether a critical number is a relative, min or max, or maybe it's neither. And it can also tell us when a function is increasing or decreasing on a given interval. So the first derivative test, we use this to determine whether a point is a relative maximum, a relative minimum, or neither. So essentially, we're going to look at our derivative and we're going to find the zeros or the critical numbers, and then we're going to see if either it changes from negative to positive. And if it changes from negative to positive, so our graph would be going down and then it's going up, that means that we have a relative minimum. Or if we see that our derivative changes from positive to negative, that means the slope of our original function was positive and then all of a sudden it's negative, that means we have a relative maximum. Or we're going to test our sign analysis and see if it's positive on both sides or negative on both sides. So meaning the signs are not changing as we cross over at C. Then that means that C is neither a relative minimum nor a relative maximum. So we really are looking for that change of sign, and then depending on whether we're changing from negative to positive or positive to negative tells us whether it's a minimum or maximum. But just remember, minimums will always look like this, so changing from decreasing to increasing, so negative slope to positive, and maximums always look something like this, so changing from a positive slope to a negative slope. And you can always sketch that out if you need to kind of visualize it on your paper. So the other thing we can use our sign analysis of our derivative, again, is to see where our graph is increasing and decreasing. So we know, again, just to generalize, if f prime of x is greater than 0, or that's another way of saying if our derivative is positive, then our original function is increasing, and if our derivative is negative or less than 0, then f is decreasing on that interval. And if our derivative is equal to 0, then it is constant on that interval. So just a sign analysis of our first derivative can tell us quite a bit about what our function looks like. All right, so let's give one of these problems a try together. We're going to look at this function, f of x equals x minus 2 times cosine of x over the interval 0 to 2 pi. So first we're going to find all of the critical numbers and their corresponding points on the graph. So remember, a critical number is where our derivative is equal to 0 or is undefined. So I'm first going to find our first derivative. So here we have 1 plus 2 sine of x. Remember, the derivative of cosine is negative sine. And we know that this function is defined for all real numbers, so it's never going to be undefined, right? We can plug in any x value we want. So I'm going to just make a note here, never undefined. So let's see when our derivative is equal to 0. So I'm going to set it equal to 0 plus sine of x. So when the sine of x is equal to negative 1/2, and we just want the values of this between 0 and 2 pi. So remember, this is going to occur in quadrants 3 and 4, because all students take calculus. So we have when x is 7 pi over 6 and 11 pi over 6. But we do want the full coordinates where those critical numbers occur. So I'm going to go back and plug those x values into our original function. So we'll find f of 7 pi over 6, which is 7 pi over 6 minus 2 times the cosine of 7 pi over 6. So 7 pi over 6 minus 2 times the cosine of 7 pi over 6 is going to be negative root 3 over 2. So if we simplify that, we would just get 7 pi over 6 plus root 3. So it's kind of a ugly coordinate. I'll write it up here. 7 pi over 6, and then 7 pi over 6 plus root 3. So that's one of the coordinates. And then we're going to plug in 11 pi over 6, so f of 11 pi over 6. So it ends up being 11 pi over 6, and then we have minus 2 times, here in quadrant 4, remember cosine is positive, so it's times positive root 3 over 2. So I kind of skipped a step here. I'm just plugging it into our function. So this value, 11 pi over 6, is 11 pi over 6 minus root 3. So that's our other coordinate. So 11 pi over 6, 11 pi over 6 minus root 3. So those are the coordinates on our graph that correspond to the critical numbers. Okay, the next thing we're going to do is figure out the intervals where our function is increasing and decreasing. So here we're going to need to do a sign analysis of our derivative. So here is our derivative, our critical numbers. Well, here's our endpoint. So we have an endpoint at 0 and an endpoint at 2 pi. And then here we have 7 pi over 6 and then 11 pi over 6. So it's definitely not drawn to scale at all. All right, so when I test values for this graph, I am going to pick strategically. So if I know I'm plugging into sine and I know I need to test something here, maybe the first thing I will plug in is pi, so f prime of pi, because I know the sine of pi is 0. So we get is positive 1, so it's positive in this region. And then maybe between these two, if you test 3 pi over 2, we know that the sine of 3 pi over 2 is negative 1. So you have 1 minus 2, which is negative 1. So our graph is negative in this region. And then really just based on what we know sine graphs look like, we know that they are cyclical and they will do something like this. So we know that it is going to cross back over. They're not touching and turning anywhere except for the max or min. So in this region, it will be positive again. So now that we have our sign analysis, we can now determine where f of x is increasing or decreasing. So again, f of x is increasing. I'll make a little note underneath when f prime of x is greater than 0, and it's decreasing when f prime of x is less than 0. So that means our graph is increasing from 0 to 7 pi over 6, and from 11 pi over 6 to 2 pi. And our graph is decreasing from 7 pi over 6 to 11 pi over 6. All right, and then the last thing we're going to look for are all of our relative extrema. So here we are looking for a sign change in our derivative. So we know that when f prime of x changes from positive to negative, so that means that our graph is increasing and then all of a sudden it's decreasing. That means we have a relative maximum. So we can look at our sign analysis. I see that it's changing from positive to negative at 7 pi over 6. So we already have that full coordinate from above. So it's 7 pi over 6 and then 7 pi over 6 plus root 3. So that's our relative max. And we know that a relative min occurs when our derivative changes from decreasing to increasing. So that's, again, when we have a relative minimum. And you can see that our derivative is changing from decreasing to increasing at 11 pi over 6. And we already have that full coordinate from above. And there you have it. So this is our relative max, and this is our relative min. So again, there's going to be a lot of sign analysis here. We're going to be finding a lot of zeros, and it is common to be working with functions that do have trig expressions, so it's going to be really important that you're very comfortable solving, basic trigonometric equations like this. So now we're going to start looking at what the second derivative tells us about our graphs. So the second derivative actually tells us about what's called the concavity of our graph. So your graph can either be, it can be concave down or concave up. So something is concave down when the slope is decreasing. So if you have a positive slope, you could see that it's getting less positive, so it's kind of flattening out like this. Or if you have a negative slope, since the slope is decreasing, it means it's getting more negative, so it's getting steeper like this. So for concave down, I always kind of think of like a sad face, and again, it's when your slopes are decreasing. So concave down, it looks like a sad face like this. And for concave up, it's when your slopes are increasing. So if you have positive slopes, they're getting more positive, so steeper. And if you have a negative slope, you're getting less negative, so your slope is still increasing. But it really just ends up kind of looking anything like a smiley face. So something like this would be concave up. And again, to me, it kind of looks like a little smiley face, so you can add that in like that. But again, it's when your slopes are increasing. So we are going to be doing now a sign analysis of our second derivative, which will tell us two things. It will tell us when our function is concave up or concave down, and it will also help us find what are called points of inflection, which is where our function is changing concavity from either concave down to up or vice versa. So here's, just kind of a picture of a graph. So here you can see our graph is concave up, and then at some point, which is called the inflection point, our graph is going to change to concave down. As you can see, it is on the right half of our graph. So we're going to use our second derivative to help us determine the concavity of our graph, which does kind of shape what our graph looks like. So for the concavity test, again, we're looking at our second derivative, and anywhere that our second derivative is greater than 0 or positive, that means our graph is concave up. And anywhere that our second derivative is below 0 or negative, that means our graph is concave down. And then points of inflection are always going to occur either where the graph, where our second derivative is equal to 0, or where our second derivative does not exist. So we're looking for those 2 points to find, again, those points of inflection. So you can see here, this is kind of what it looks like when our second derivative is equal to 0. It would look something like this, and you can see that our graph is changing from concave down to concave up. Or sometimes your graph changes like this, and this is when our second derivative does not exist. So here you're concave up, and then here we're concave down. So we're looking for these two cases to help us find those points of inflection. And then here is just another definition of concavity. So we say that a graph is concave down when our graph is falling below our tangent line at any point. So if you look in this region right here, if you drew a tangent line at any point like this or here, you could see that our graph is always going to be below it. And then our graph is considered concave up when the actual graph would fall above the tangent line. So you can see any region here, if you drew a tangent line, your graph is going to sit above it, except where it is crossing at the tangent line. So that's another definition of concavity. All right, so let's try another example together. Here we're going to consider that same function from our first example, and we're going to first find the intervals of concavity, and then we're going to find any points of inflection. So if you remember, our first derivative from example 1 was 1 plus 2 sine of x. So that means that our second derivative is 2 cosine of x. So remember, for the points of inflection, to see where it changes concavity, we're looking for when our second derivative is 0 or undefined. This will never be undefined, so I'm going to make a little note, never undefined. So we will first look for when our second derivative is equal to 0. So whenever the cosine of x is equal to 0 within this interval, so we know that that occurs at pi over 2 and 3 pi over 2. So now we just need to do a quick little sign analysis to figure out where our second derivative is positive or negative. So here's our endpoints. Here's pi over 2 and 3 pi over 2. So we know that cosine is always positive in quadrant 1. It's negative in quadrants 2 and 3, and it's positive again in quadrant 4. So then wherever our second derivative is positive, we are concave up. So that's from 0 to pi over 2, and then 3 pi over 2 to 2 pi. And wherever our second derivative is negative, we know that we are concave down. So that's from pi over 2 to 3 pi over 2. So those are our intervals of concavity. And then our points of inflection, we do need to take these points and actually plug them into our original function to get the full coordinate. And remember, for points of inflection, we are looking for that change in sign. And it does change over at pi over 2 and 3 pi over 2. So those would both be values for our points of inflection. So let's find f of pi over 2. So we have pi over 2 minus 2 times the cosine of pi over 2, which is 0. So pi over 2. So this coordinate is pi over 2, pi over 2. And then let's find f of 3 pi over 2. So again, it's 3 pi over 2 minus 2 times 0 again. The cosine of 3 pi over 2 is 0. So it's just 3 pi over 2. So we have the coordinate 3 pi over 2, 3 pi over 2. And these would be our 2 points of inflection. So the last thing we're going to talk about is yet another way that we can test for a relative min or max. So remember, the way that we've already talked about today is determining when your derivative is equal to 0 and then seeing if it changes from positive to negative or negative to positive. The second derivative test is another way you can see if a critical point is a min or max. So first, we do need to make sure that the first derivative is equal to 0. And then if at that point the second derivative is greater than 0, meaning that it's concave up, then f has a local minimum at that point. And if f prime of c, again, if your first derivative is equal to 0 and your second derivative is less than 0, meaning concave down, that means you have a local maximum at that point. I do want to point out that if your second derivative is equal to 0, so it's not greater or less than 0, then this test is inconclusive, meaning we can't use this test to determine if it's a relative min or max. So in that case, we would have to go back to that first derivative test to decide. All right, let's give this last one a try together. So here we're going to try to find the relative extrema using our second derivative test. But first we need to find those critical points, which is where our first derivative is equal to 0. So we'll start by finding our first derivative and setting that equal to 0. So we have 4x squared times x minus 3. So our critical points are at x equals 0 and x equals 3. But again, we need to know that in these regions, or at these 2 points, is our second derivative positive, negative, or maybe it's 0, so telling us we can't use it. So let's find our second derivative. So we have 12x squared minus 24x. So we do need to do a sign analysis of our second derivative, because remember, we want to know whether it's positive or negative, whether it's concave up or concave down. So we would want to find the zeros of our second derivative so we can see when it might change from positive to negative. So we see that these zeros are at 0 and 2. So now we can do our little sign analysis. If you plug in -1, we get a negative times a negative, which gives us positive. Let's plug in maybe 1, we get a positive times a negative, which gives us a negative. And if you substitute 3, we get a positive times a positive, resulting in a positive. So here you can see the different intervals where our second derivative is positive and at negative. So we can see that at x equals 3, I'll make a note over here. So at x equals 3, our second derivative is greater than 0. So that tells us that our graph is concave up. So it looks something like this. So if something is concave up, that means that we actually have a relative minimum. So at x equals 3, we have a relative minimum. So that's part of our answer. But then if you look at our other critical point at x equals 0, we can see that our second derivative is also equal to 0. So at x equals 0, f double prime is equal to 0. So that means our test is inconclusive. So we can't tell with our second derivative test if it is a minimum or maximum or maybe neither. So just to give us a little bit of clarity for what's happening here, let's actually look at the original function again to see what's going on. So if you factor this function, let's say we were trying to graph it, we'd have f of x equals x cubed times x minus 4. So you can see for this graph, we have a multiplicity of 3 at 0. We have that triple root. And here's the other 0 at 4. So that tells us at x equals 0, remember with triple roots, our graph kind of slows down, but it keeps going. So it turns out at x equals 0, we have neither a relative minimum nor a maximum. And then here's when x is equal to 3. That's when we have that relative minimum. So here we would determine that it is actually neither. And another way that, again, we could determine that, we can see in the graph that it's neither, but we can go back and we can do our first derivative test. So we can do a quick little sign analysis here of our first derivative, whose zeros were at 0 and 3. So if you plug in -1, we get -1 squared. So this one is positive, and this is a negative, so that gives us a negative. And if you plug in 1, we get a positive times a negative, so it's negative. And then maybe if you plug in 4, we get a positive times a positive. So you'll see that at x equals 0, our first derivative actually doesn't change from positive to negative or vice versa, which is why we have neither a maximum nor a minimum at x equals 0. So we can either kind of graphically look at what is our function doing. Sometimes that's easier. Or again, we can use that first derivative test, and we're looking for that change of sign of the first derivative. All right, so that is all for today's lesson. Thank you guys so much for watching.